Hey, Algebra 2, welcome back. Here is 7.4b, just continuing our little study of logarithms, our introductory uh, introduction, not introductory, introduction to logarithms, okay? We're going to describe the relationship between the logarithmic and exponential functions a little bit more, and then we're going to graph some transformations of the logarithmic function, okay? So just kind of furthering a little bit of our information on this new function that we're learning about, okay? And then in 7.5 and 7.6, we'll talk about properties and solving equations and all that good stuff. Okay, but first we need to set a good foundation. Okay, so just remember kind of what we talked about in 7.4a, that little relationship between our exponential and our logarithmic, right? B to the power of x equals y is the same thing as log base b of y is equal to x. Okay, and remember these two are inverses of each other. Remember that the logarithm and the exponential are inverses of each other. So here in this first example where it's asking us to find the inverse of each function below, we have an exponential function here. You can hopefully kind of guess, since exponential and logarithmic are inverses of each other, this is gonna end up, our answer is gonna end up looking like a logarithm. Vice versa, here we're starting with the natural log. We're gonna have something that looks like an exponential. Okay, so let's kind of take a look at and see what that is gonna look like, okay? Do you remember how to find the inverse, right? So our first step is to write out the equation using y. Our next step is to switch the x and the y. So I get x is equal to 6 to the power of y. And then I need to solve for y. Okay, here, how do we solve for y? No idea, right? The way we're going to do this is by using this little thing up here. Okay, b to the x equals y is equal to, I can rewrite that as the logarithm. Okay, so I'm going to set it up the way I have here. I'm going to put the exponential on the left-hand side, and then I'm going to use my little circle trick. Okay, log base 6 of x is equal to y. And that's what I want. I want y equals something. So y is equal to log base 6 of x. Okay, and I did that using this up here, using the little circle trick, right? Log base b of y is equal to x. It's a little like it's a little confusing here with the x and the y being in the different places. Just remember that our input and our output switches. Okay, our input here was y, our output was x. So now our output is y, our input is x. Okay, so our inverse function here is log base 6 of x. And that's kind of what we had guessed earlier, right? We had guessed that it was going to have something to do with a logarithm. Looking good. All right. And then the next example, I have natural log of x plus 3. Same thing, I start by writing down the equation with y, natural log of x plus 3. And then I switch my x and my y. So x is equal to natural log of y plus 3. Same thing here. I have no idea how to get that y out of there. So I'm going to rewrite it as an exponential. Okay, I'm going to kind of switch this. I'm going to put the logarithm on the left-hand side. Equals x. Sorry. This should be a y. Equals x. And remember, it's ln natural log, so my base here is e. So if I do my little circle trick, b to the power of x is equal to y. So e to the power of x is equal to y plus 3. E to the power of x is equal to y plus 3. I have to solve for y, so the last step here is to subtract the 3. So I get y is equal to e to the x minus 3. So then my inverse function is e to the power of x minus 3. Okay, that I totally botched that right there. That's a lot better. Okay, so those are our inverse functions. And you kind of see the direct connection now. We had been talking about how exponential and logarithm are inverses of each other. And now we see that concretely because we did it algebraically. We kind of proved it a little bit, not super formally, but we showed some examples where, yeah, that's true. Natural log, inverse of it is e to the x minus 3. Exponential with base 6, the inverse of it is a logarithm with base 6. okay? Now let's take a look at that graphically. Okay, we showed it algebraically. Now let's see what that looks like graphically. Okay, so we're going to graph f of x equals 2 to the power of x and g of x equals log base 2 of x on the same axes. To do this, let's go ahead and let's do some tables. Let's kind of set it up in a table. And so I'm going to start by doing my f of x. So I have my little x and y column here. And here's f of x. So my 2 to the power of x here. I'll just do some nice x values, 0, 1, 2, 3. Okay, and so what do we get from 2 to the power of those numbers? Well, 2 to the 0 is 1. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power is 8. Okay, now the next thing I want to do is make a table for g of x, but I don't have to. Do you know why? Because remember, for an inverse function, all we have to do is switch the inputs and the outputs. Okay, switch all the values from the inputs with the values from the outputs. And since we know these two are inverses of each other, that's all we have to do here. So 0, 1 becomes 1, 0. Whoa, I did that in the middle, smack dab in the middle of that column. 1, 0. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. And 3, 8 becomes 8, 3. Okay, easy peasy. And now let's go ahead and graph this. Okay, so I'm gonna go ahead and do this. Okay, I think that's enough. At least we'll see if it's enough. And then that should be enough. Okay, so I was just trying to scale out enough because I need 8 on my y-axis and my x-axis. So we have 1, 2, 3, 4, 5, 6, 7, 8. Yes, I did it. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I went a little bit extra over here, but that's okay. Okay, so now let's graph these points. I'll do it in different colors to show you the distinction. So I'll do my exponential in green. I have 0, 1, 1, 2, 2, 4, and then 3, 8, all the way up here. Okay, and remember the exponential looks kind of something like this. Try not to butcher it too much. Something like that, right? There's our exponential function. And then remember, the exponential has a horizontal asymptote, right? It has that horizontal asymptote at k. Here there's no k value, so it's at 0. So it's at y equals 0. All right, so now let's do the logarithm. So I have in blue, I have 1, 0, 2, 1, 4, 2, and then 8, 3. Okay, I'm gonna push this down a little bit here. And so this one is doing something like this. Hey, that was actually not too bad there. Okay, there's our logarithmic function. And it totally makes sense with our idea of inverses, because remember, for a graphical inverse, those graphs are reflected across the line y is equal to x. Okay, and you can totally see how these two are mirror images of each other, even down to the asymptote. We're going to talk a little bit about here how logarithms, logarithmic functions, they have vertical asymptotes. Okay, this one, the base one, is x equals 0, since there is no h. Okay, and we'll talk about that more here in a little bit. But you can definitely see now graphically as well that, yeah, these two things are inverses of each other. Okay, I'm a math person, so I think that's pretty cool. Maybe you don't. Maybe you can just pretend to think it's cool for me. But yeah, that's kind of the idea behind these two, okay? Now let's go ahead and sketch one more of these logarithms using our general logarithmic form. So kind of like how we had a general form for the parabola, for the rational function, for the radical function, for the exponential function. Now we have one for the logarithmic form. Okay, so that's going to be f of x equals log base b of x minus h plus k. No a this time, no stretch or shrink factor, because we don't really care about that for logarithms. We're mainly focused on the left, right, up, down movement. So we're just going to kind of not really worry about a for now. So you know what h is, you know what k is. We'll just quickly review. Our h is our horizontal translation. Our k is our vertical translation, right? Now let's talk about domain range. Okay, remember inverse definition is we switch the domain and the range. If you remember from exponential, the domain of the exponential was negative infinity to positive infinity. So now it's going to be the range of the logarithmic function. And that's going to be in always, right? And our domain, the range on the exponential was the one that changed changed all the time. Now it's the domain. The domain is the one that varies. And now we had a horizontal asymptote reflected across y equals x. That becomes a vertical asymptote. It's going to be at x is equal to h. Okay, it's no longer y equals k, it's x equals h. All right, let's finish this off. Describe the transformations we see in this function. Log base 2 of x plus 3 plus 1. Then we'll sketch a graph, doing the usual stuff, right? Labeling our intercepts and vertical asymptote, and then stating our domain and range. Okay, so what do we see in this function here? We see our h is equal to -3, and our k is equal to 1. Okay, so a -3h, that means shift left. I'm like mixing up, there we go, left by 3. And then our k being 1 means shift up, up by 1. I'm just misspelling all my words today. Cool. So now we're gonna call on Desmos to help us out here to get a sketch. Okay, so here's how we're gonna do it. We have, go ahead and open up this little keyboard. Okay, we have log base 2. So go to functions. We're gonna need to use this one right here, log base a, so that we can get that base of 2. So click there, and then I can put a 2 right there, and then I can use this right arrow key to move out to the parentheses. X plus 3, close parentheses, plus 1 on the outside. And there's our nice logarithmic function. Okay, make note of our intercepts. We have one at -2.5 and one at 2.585. And then here, our asymptote, I cannot recall if this will let me do a vertical line. X is equal to -3. Oh, it does, yeah. So our asymptote is x is equal to the h value. Our h value is -3. So there is our asymptote. And let me make it dotted here. Cool, so there's our fully realized logarithmic function. Okay, so let's just go ahead and sketch that, labeling our intercepts and vertical asymptote. Okay, so go back to the whiteboard. Okay, I think I'm gonna need, let's say, there, give myself a little bit of room. I think to there if I can count properly. Nope, one more. And then we're just gonna start over. Boom, and then this much. Okay, one thing that you guys will learn about me is I have terrible spatial awareness. That's okay. So then I'm just gonna take this off by ones. So ones, ones, ones. Okay, so 1, 2, 3, 4. And then you get the idea for the rest of them, right? That's all scaled by ones. Okay, so we have a vertical asymptote at x is equal to h. We have one at -3. So vertical asymptote is x equals to -3. So I'm going to draw that and label it, right? X equals -3. And then I have an x-intercept at -2.5 comma 0. And then I had a y-intercept at 0 comma 2.585, so a bit more than 2.5. So I have one right here, and I have one right about here. Okay, and there's going to be our graph. It's going to follow that same shape, right? Aside from the intercepts, the rest of the shape of the graph doesn't have to be too perfect, right? As long as it has that logarithmic shape, right? Very cool. And so this intercept right here is 0.250, comma 2.585. I can speak. And this one is -2.5 comma 0. Last but not least is our domain and range. Okay, we know one of them. Our range is -infinity to infinity. What's our domain? Our smallest x value is -3, left parentheses because it's not actually touching it because it's got an asymptote, and it travels all the way off to the right to infinity. Awesome, you guys. Okay, so that's it for 7.4. Did a lot with logarithms. We're going to keep on doing a lot with logarithms for the rest of the chapter. Okay, so make sure you're asking your questions if you're not understanding. This is a hard chapter, so don't be upset with yourself. Don't be scared to ask questions. I am here to assist you. Okay, have a good rest of your day. I'll see you in the next one.